This week, we will talk about multiple linear regression. We will review regression coefficients and significance test, ANOVA table and F-test, R-square and significance test. We will continue talking about delta R-square and multiple correlation in multiple regression. Then we will introduce model comparison. This includes nested models, full and reduced model, and how to conduct model comparison by hand and by SPSS, how to report the results in APA styles. Finally, we will summarize by 3 perspectives on multiple linear regression. We have introduced this example before the low residency program. We talk about when we spend more money on education, this will lead to better prepared high school students. The dependent variable is SAT, and there are 4 independent variables: expand, the pupil-teacher ratio, average teacher salary, and the percentage of students in that state that take the SAT exam, the percent SAT variable. We constructed the correlation matrix. However, if you look at the correlation among these 5 variables, SAT was negatively related to expand. It was also negatively related to salary. It was strongly negatively related to percent SAT. There's something going on between SAT score and the state that most or less students taking the SAT test. Therefore, to truly understand to what extent expand would predict SAT score, we need to examine the predictive value of SAT. Well, keep the percent SAT constant. Basically, we are looking at one predictor while controlling another, in this case, percent SAT constant. We can do this by regress SAT on expand for each fixed percent SAT score. Therefore, this coefficient is independent of percent SAT. For example, when percent SAT is 40, we can regress SAT on expand have B1. For percent SAT is 60, we can regress SAT on expand again, have B2. We could do this for all possible values of percent SAT. We will have theoretically a limit number of B's. Each of the B values is independent of percent SAT. Each of the B values is not affected by the variable x2, percent SAT. Now we can take the average of all the above B's. This averaged B will be independent from the effect of percent SAT. And that is the gist of multiple regression. We are looking at the relationship between expand and SAT while holding percent SAT constant. Next, we run multiple linear regression with SPSS. You can download the data file MLR _SAT from Canvas. First, you look at the dataset examining the sample size, data range, missing data. I've already done the log transformation of percent SAT because this variable is skewed. You can run multiple linear regression again. Click on Analysis, then Regression, then Linear. Move Expand into Independence. Click on Next. Move log % SAT into Independence. Then move SAT into Dependence. Click on Statistics, check Descriptives, click on Continue, then OK. Here is the SPSS output, the model summary, ANOVA, and the coefficients. It displays two models. Model 1, we regress SAT onto expand. So model 1 only has one predictor. It is a simple linear regression. Model 2, we regress SAT onto both expand and log % SAT. So model 2 has two predictors. It is the multiple linear regression. Let's look at the coefficient table for model 2. The coefficient table and the t-test for regression coefficient model 2 will have both expand and log % SAT in predicting SAT score. Here is the coefficients table. It has both model 1 and model 2. Here we focus on model 2 only. The dependent variable is SAT. And we have two independent variables, expand and log % SAT. This is the slope. This is a B1 for expand. This is B2 for log % SAT. We can construct the regression equation y hat or predicted SAT equals to 11.13 times expand minus 78.205 times log % SAT plus 1147.100. This is the multiple regression equation. Looking at the t-test for expand and log % SAT, both t-tests are significant. Therefore, both expand and % SAT significantly predict SAT score. Expand significantly positively predicted SAT score, while log % SAT significantly negatively predicted SAT score. The second table is the ANOVA table and the F-test for R-square. Here we have model 2. We have both expand and log % SAT in predicting SAT score. The top part is the ANOVA table produced by SPSS. We can look at this ANOVA table and understanding each component of it. This is for model 2. And if you look at the sum squares for total, SS total equals to sum of squares of y. It is 274307. DF total equals to sample size minus 1. It is 50 minus 1, which is 49. SS residue is 31241. DF residue is n minus the number of predictors minus 1. So it is 50 minus 2 minus 1, which is 47. Mean squares residue equals to SS residue divided by DF residue. It is also called residual variance. It is 31241 divided by 47, which is 644.719. If you look at the sum of squares for regression, SS regression equals to SS y hat. This is 243065. DF regression equals to number of predictors, which is 2. MS regression equals to SS regression divided by DF regression. So it is 121532. F-test is the ratio of MS regression and MS residue. It is 182.834. Next, we need to find out the F critical score. DF between is 2. DF within is 47. So we look at 2 and 40. F critical score is positive and negative 3.23. We compare F critical score positive and negative 3.23 with the F score. F observed score is greater than F critical score. Therefore, our model is significant in predicting SAT. F parenthesis 1, 47 parenthesis equals to 182.834. P is less than 0.05. Finally, we look at the model summary table with the R-square. Again, we focus on Model 2. In this model summary table, first we look at the R. R is 0.941. This is a correlation among expand, log percent SAT, and SAT. It is called the multiple correlation. R-square, if you square 0.941, you will get 0.886. This is the amount of variance in Y that is explained by both x1 and x2, 0.886. The formula for R-square is SS regression divided by SS total. So the top part is the variance predicted by x1 and x2, and the bottom part is the total variance in Y. Therefore, if you look at the ANOVA table, you got these two numbers from SS regression and SS total. R-square is 0.886. Next, we need to conduct a F-test to examine if R-square is significant or not. This F-test is the same test we did in last slide. F equals to MS regression divided by MS residue. If you look at the ANOVA table, there are these two numbers. F score is 182.856, and it was significant. P-value is less than 0.001. Our conclusion is that our model is significant in predicting SAT. R-square is 0.886, F is 182.856, P is less than 0.05. We talked about what R-squares mean. R-square equals to SSY hat divided by SSY. SSY hat is also SS regression, sum of squares for regression. So the bottom part is total variance in SAT, and the top part is the variance in SAT that is explained by both x1 and x2. Therefore, 0.886 means that using both expand and log percent SAT, we can explain 88.6% of variance in SAT scores. at the Model 2, we regress SAT onto both expand and log percent SAT. We have three tables: coefficient table, ANOVA table, and model summary table. What does this output mean to us? First, we look at the B weight for percent SAT. It was significant. Then we look at the B weight for expand. It was also significant. So both predictors are significant while in different directions in predicting SAT scores. So predicted SAT or SAT hat equals to 11.13 expand minus 78.21 log percent SAT plus 1147.113. Now we look at the model summary. R square is 0.886. And the F-test for R square was significant. Now we have two predictors. The F-test tells us if the whole model with two predictors is significant, while the two t-tests tell us if individual predictors are significant. Now we can report the complete results in AP style. Expand significantly positively predicted SAT score. B is 11.13, T is 3.41, P is 0.001. Log percent SAT significantly negatively predicted SAT score. B is negative 78.21, T is negative 17.49, P is less than 0.01. Finally, our overall model was significant. R square is 0.89, F is 182.86, P is less than 0.001.